Gravity is a force that is all around us, and is a building block for galaxies and the universe itself. The weakest of the four fundamental forces of nature, yet the force that holds all mass together. It holds us onto the earth and causes stars to ignite. Quite simply, it is essential for the universe as we know it. Any object with mass will project a gravitational field around itself. A smaller object placed in the field of a more massive object will be attracted to it. Let's say, for example, a satellite orbiting a planet. Both the satellite and the Earth will exert an equal but opposite force upon the other. The line of action of which the force takes is called a field line. These differ in the two types of gravitational fields, radial and uniform. In a radial field, the field lines act towards the centre of mass of the object. In a uniform field, which can be assumed at the surface of the planet, the field lines are parallel to each other, so 90 degrees to the ground, and all act in the same direction. For an object trying to escape Earth's gravity, such as a rocket, it encounters different levels of gravitational potential as it does so. Field lines have equipotentials surrounding them, which decrease the potential as you move further away from the planet. The gravitational potential is defined as the work done per unit mass to move a small object from infinity to that point. Over a small distance, the potential gradient equals delta V over R. We can also use this to find the gravitational field strength, as shown by G equals minus V over R. Isaac Newton is basically the father of modern physics. He came up with the theory of gravity, and his law of gravitation has allowed us to predict the positions of planets in our solar system and was used to send men to the moon. His law states that the force acting between two objects with mass is equal to the gravitational constant multiplied by the product of those two masses over the radius squared. The force is therefore inversely proportional to r squared and proportional to the product of the two masses. As an object moves away from a planet's gravitational field, the strength of the force acting on it decreases. For planetary fields, the strength of the force acting on a projectile is F equals gm of the planet, m of the object, over r squared. For gravitational field strength, we can ignore m, the mass of the smaller object, as it can assume to be negligible compared to the mass of the planet. Incidentally, inside a planet, you would expect the gravitational field to carry on increasing, but, as shown by the diagram, it actually decreases. Gravitational potential also decreases. It is negative to show it's a vector and an attractive value. It's given by V equals minus gm over r. For a mass orbiting a larger mass, we can say that its velocity is at a right angle or tangential to the orbit's path. We can say that the force is directed towards the larger object, so in this case the Sun, and the radius is just the distance between the Sun and the object. For satellites, geosynchronous satellites orbit around the equator of the body that they are moving upon, and their time period is equal to 1 day or one full rotation for that planet. For an object in orbit, the force acting upon it is equal to the square root of 4 pi squared r cubed over the gravitational constant times by the mass of the larger object. Its energy is given by minus 1/2 gmm over r. The velocity of an object orbiting a planet is given by the square root of the gravitational constant multiplied by the mass over r.